Well, thank you very much. And it's a real joy to be here amongst all the people that I recognise from when it all started, and particularly amongst the students that I'm currently supervising. I can see them currently sitting around. So thank you very much for inviting me. So what am I going to talk about today? Well, for a change, I'll talk about uncertainty. And I want to say, uncertainty, nothing is more certain. And that was a phrase by a Roman gentleman some 2,000 years ago called Pliny the Elder. But I think it's really relevant when we think about it today. And so I wrote a paper together with the New South Wales chief scientist about this topic, about uncertainty in the environment. And I'm going to use this analogy of uncertainty, or not the analogy, but the discussion of uncertainty, to point out what I think, how we have made successes and where we need to go. So this was at the beginning, right? At the beginning, there was DARE, and DARE looked like this. And as you can see, I put it in red. One of the key features of DARE was recognising the challenges that people face in the environmental sector when it comes to making decisions. So to quantify, explain, and understand uncertainty. It was actually, I wanted to actually call it RISC initially, which stood for the Research Institute for the Scientific Quantification of Uncertainty, which I thought was pretty cool, but I was convinced otherwise. So that's what we really want to do. And this is the point of data science to me. The point of data science is so that we can learn from data to make robust and justifiable decisions. And at the heart of all that decision-making is uncertainty, which is why it is so important. Now, and I've got this question mark in the middle because I really feel quite strongly, what have I learned since I've moved away from writing, I loved writing maths and stats papers, but moved into the more multidisciplinary area. It's very much, if we want to have impact, we need to start with the problem. So that very focus on what question you're trying to solve or what decision you're trying to make is important. Obviously we start out, we have some knowledge and beliefs. I'm not going to go through too much of this. You've probably all seen this before. However, here I do want to point out that we go and hopefully get some data that will help us answer the particular question. And the data that we get is not necessarily big data. So I'm not a huge believer in big data. I'm a big believer in useful information. And there's a lovely quote by a statistician in America, a very famous one called Nate Silver, where he said, the amount of truth is approximately constant, irrespective of the volume of data that we collect. And so I think that that's a very useful thing to keep in mind when we're trying to really seriously tackle questions in the environment. We have models, and we've had a lovely display of all the models already, and I look forward to seeing more, but obviously models, knowledge and decisions. So that's what was sort of behind DARE to begin with. And this actually was a slide, when I went to put this together, this is a slide from the launch. And it was all the way back in May the 20th, 2021, and this is what it looked like. And it seemed really apt at that time to be doing this because we just got through some of the worst droughts we'd ever seen. You can see there in 2019. January the 5th, most people here that were in New South Wales will remember those terrible, terrible fires that raged and the destruction that it did to the environment. And before we knew where we were flooded literally a month after, and then we had 4 years of rain. And in the meantime, COVID broke out. So all this idea about the future is really a little uncertain, and how we deal with and making decisions is really important. And I'll just put this up because these were the gang at the beginning, and you can see how much I don't want to say it, but, I looked at this and I thought, oh, they look so young. And I thought, what have we done to them? What have we done to the students over the years? Because they look considerably wiser, I will say now. But that's how they looked at the beginning. And that was the group that we began. But let me go back to these decisions. Here's a decision. How high? What do we want to build Warragamba Dam? We need dams because the supply of water via rainfall is highly more variable than the demand for it. That's why we have dams, right? So to try and manage that inconsistency between supply and demand. This was another project that I worked on with the New South Wales chief scientist, which was What is the, how many horses can the national park sustain? How many should we kill because of their impact on their natural habitat? Or here was another one, where to drill, okay? Where to drill for thermal energy. Thermal energy is when you hit granite and it's got a temperature gradient, and that you can use for clean energy. And then the thing that we don't know about is the subsurface geology. So this is trying to connect the decisions, because ultimately I think that's what, you know, data science is useful for, to help people make better decisions, and connecting those decisions to things that are unknown. Okay, so now we come to uncertainty quantification. As I said, I'm going to go through what I think of uncertainty quantification, and in that I will keep coming back to what I think are the areas of future research going ahead, and where we've done well or not done well. And this was a quote. There was an article in Biometrika. This was from, you know, Noel Cressy, and you can see he thinks that uncertainty, you know, is best served by a Bayesian hierarchical model. And that appeared, I think, in 2023. And in the same issue was our article that also appeared. So if you ever wondered why DARE had a Bayesian flavour, I think this gives you the idea. In fact, the students used to call it the Bayesian temple, because that was sort of the paradigm that we were working in. And I think it is a good paradigm to work in when you're talking about uncertainty. So I'm going to go through, in our article, we sort of had a taxonomy of uncertainty to help us think about how data science may help us with these various levels of uncertainty. And so the first one is aleatoric uncertainty. That's when it doesn't matter how much data you have, there is some inherent randomness in the future. And I'm not really going to talk too much about that, because that's the things like the outcome of the toss of a coin. How much uncertainty there is in that, you know, is not really going to be changed by you tossing the coin more times, right? So presumably, I mean, you can imagine a world where you could construct it, but okay. But now we get on to things that I think statistics and data science can help with parameter uncertainty, right? So, and that may be the density of a rock in a layer in, you know, when we're looking for geothermal energy. Model uncertainty, and that may be, so we've got a model of what that underground structure looks like, right? So how confident we are in that model. So we had RPIT talk about a whole bunch of ODEs and PDEs, and I've got an example with those. They're models, right? Are we confident that they are the right model? Could it be some other model that is the right model? And finally, what I call knowledge uncertainty. Now, this is uncertainty when really you simply don't know. And this is what we were in the position of with the wild horses in the Kosciuszko National Park. We simply did not know. And so, you know, that was the equation, and they correspond to the various levels of uncertainty. The first one there is the aleatoric uncertainty. That is a future observation. I'm assuming I've got all the relevant data. I know the model is just uncertain. The second one is parameter uncertainty. The third, of course, is model uncertainty. And so the next question was, you know, how can probability adequately describe these levels of uncertainty? And I would say most definitely yes for the first three, right? So we can start to understand the uncertainty we face by trying to do something with probability. But I would, the fourth is, in fact, it's really defined by the fact that we cannot, you know, we know so little, and this is the position we were in the beginning of COVID. We know so little that actually starting to talk in probabilities is a bit misleading, because it gives the appearance we know what we're doing, and sometimes we don't. And I'll talk about how we might proceed when we're in those types of situations. So let me just go through this. Don't worry about the specifics. So this was a project that was started off, and one of the things that led to DARE, and we are trying to uncover what the subsurface structure looks like in the Cooper Basin. The reason that we're trying to do that is we're trying to find where granite is, right? Because granite will deliver that geothermal energy. So we've got a model. Now, here is an interesting example of what I mean about useful information and not big data, right? So we've got a lot of sensors at the surface we can collect. You know, I think I've listed them there: gravity, magnetic tellurics, magnetics, seismic data. All of that we can collect on the surface, but that is not the quantity of interest. The only data that really tells us about what's underneath is from a core sample. So you can collect all this data on the top, but it may tell you something, a little bit of something, but it is not really increasing our knowledge as much as if we could take core samples. So there's an example, and of course this is why this area is so difficult, because it's an inversion problem. You see things on the top and you're trying to infer what were the rock properties underneath that led you to see that. So point number one is, we need better algorithms. And I think Willem mentioned that at the beginning. I'll say this was in this paper. There's a series of Markov chain Monte Carlo algorithms with varying transition kernels. I'm not going to go into what that means, but most people here will know that all those histograms of that parameter estimate should look the same. That's the theory, right? So after you've burnt in enough to a chain, those parameter distributions should look the same. And this is just one problem. This is just this is not a high dimensional problem. And you can see that they're different by comparison to that exactly the same model, exactly the same data. The only thing that's different in those first top three is the transition kernel in the MCMC. So we still have a way to go before, I think, particularly in complex models, as opposed to, and by complex, I mean high dimensional models, where we can actually guarantee that what we're getting out of MCMC schemes is meaningful. So that's the geothermal one. Just to give you another example of where we're sort of lacking in algorithmic development, here is an example of another paper that we're interested in here about landscape evolution. And that's actually the particular landscape that we were interested in. There's a series of PDEs in this case that describe how the height of the landform changes over time, right? So the important thing here is those series of ODEs or PDEs in this case actually correspond also to a graphical model. So you can go from an ODE and a PDE to a graphical representation of it. That is actually saying you know what the model is and you're just trying to estimate various components of that model. And here we were interested in estimating what was the rainfall like about 500,000 years ago and what was the erodibility of the rock 500,000 years ago. We were looking at it from that point of view. And there's a picture of the joint posterior distribution of the rock, of the erodibility of the rock and the rainfall. Now, what's gone on, and it took us ages to figure this out, but it's because we've taken a continuous process and we've discretized it. So this is sort of numerical errors in the discretization process. So we heard about replacing ODEs and PDEs with neural networks, right? But as Arpit also acknowledged, that does not impose, that just penalizes you from being far from the solution to the ODE or PDE. It doesn't guarantee that those things are met. And also the neural network is never really going to tell you in the way that a physics equation does about, causal structure. But the question is it the right causal structure? That's another issue. So maybe we're getting this because we got the wrong model. All right. So, and now so just my last example in this is trying to figure out a parameter uncertainty for the horses in the national park. And this was not even a posterior. We have almost no data at all on this. And we came up to the conclusion that it was probably about 15,000, and that was because the lowest reported number was 9,000 and the highest reported number was 22,000, and so the number that was reported in the press was 15. A very large error bar, right, about what does that, and yet this was used in decision making, right, with ignoring the fact that that could be anywhere between those two values. Okay, so let me move. So just to recap, I think when I look at parameter uncertainty, I think we need better algorithms. And the last point around the horses was we need to start collecting an actionable database that is in some way answering a question of interest rather than just collecting the data for its own sake. We need to go out with a question and figure out what is the most useful data that we need to collect that. So now I'm just going to move over to the second type of uncertainty, model uncertainty. Now, model uncertainty is really hard, actually, because there are a lot of possible models, and the posterior distribution of the models is discrete, so you've got that normalizing constant on the bottom, and you have to enumerate over all possible models. It's almost impossible to do most of the time. And so what we do is compare the relativities of one model to another. So probability of model 1 given the data over probability of model 2 given the data. Now, this is a really good thing to do if you think that models 1 and 2, of course, we all know all models are wrong, just some are useful. If models 1 and 2 are useful, then having a sense of the relative likelihood of each of them is a really useful thing. But what about if models 1 and 2 are just so they're rubbish? So they're not even close to the truth. And as you see, that's where we are sort of at with the horses. So just to go back, so here is my model, here's my PDEs, here's the model. You know, by saying what is the model, I'm taking away all those arrows, right? I'm saying I don't know how all these, I can measure them, but I don't know how they're connected in any way. And that is a really tricky computational problem. If we really don't have physics and we're just trying to connect those edges in some way, and this is an area that my current area of research, this is a very difficult problem. So model uncertainty is difficult. So here, for example, I've just given you an example of the horses. You know, these may be things that affect the horses. Rainfall, for example, will affect sort of all species. You know, more rainfall, more grass, more reproduction of all species. It may look something like this, or it may look something like this. And in fact, the total number of ways that you can connect all those things in what's called a directed acyclical graph is approximately 2 to the 45. That is more ants than there is on the planet, and there is no computer that can, at this point, in a finite amount of time, exhaustively enumerate that. So we are constantly trying to develop algorithms which hop between models of hopefully high probability, but our research has found that that's really we're not doing a really good job of it. So that's another area of research. Now we come to the last area. And I wish, you know, I had read David Spiegelhalter, who is the most fantastic writer. He's also a very good probabilist. He's you know, one of the top people in the UK. And he's written a book called The Art of Uncertainty. And he very smartly, as we all know, there's some sort of obsession in the AI community with this construct of depth. And maybe it's because there's a lack of it. But so what we call knowledge uncertainty, he calls deep uncertainty. And I think that's a very good, because we really don't know a lot of the time with the amount of uncertainty that we're facing. And as I've said, you've got no idea what a model is, right? So if we look at how do we deal with, you know, knowledge of uncertainty, and this brings me to the last point I want to make about what I think is, you know, really is a challenge in the future. So what we argued in the paper, well, you probably know something. So start with what you know. And in this instance, it was that 350 horses could get homed per year, right? So we were pretty confident that that was a number. And then the next step was to say, okay, so then the number of horses that will give, you know, what population will give a maximum of 350 new horses each year, right? So, and that's where the figure of 3,000 came up. So we had then a figure, so 350 horses can be rehomed each year, means we need to have a maximum of 3,000 wild horses. So start with what is known, then establish what you do know about parameters, uncertainty, model uncertainty. So a parameter uncertainty is the number of possible horses, right? So, and here is where actually some really interesting, you know, and to use the deep tech, like to use drones, to use image analysis, will be very helpful in establishing this. So this is an example of where, you know, those types of technologies are really, really useful. So again, damage caused by horses, monitored over time from images taken by drones and analysed, you know, using deep learning algorithms. So this is an example of establishing that. And then this leads me to my last point, which is ultimately, I'll come back to my first point, is we need to start with the problem. And we need to intelligent data acquisition strategies. So we need algorithms which tell us what we don't need, what we don't know, and to actually work on collecting the data that will resolve our uncertainty the most. Now, I know that Edward is going to talk much more about this when he gets up, but here is just an example of what we call an information utility gain. So if acquiring or reducing our uncertainty is what we want to do, then that suggests a data sampling strategy that will maximally reduce our uncertainty in the fastest possible time. And this is another area which I think we're just starting to come to grips with now, and it is very exciting. So does it really matter? Well, I hope I've convinced you that it does. Not always, though. Sometimes all we want to do is predict, and that's fine. And then all the neural network-based architecture algorithms are fantastic, right? So, but where is prediction only? Under what conditions do we only want to predict? Well, where there's lots of data, because they need lots of data to train, where decisions are reversible. So if we stuff up, we can easily reverse it. If you price Coca-Cola at the supermarket by the wrong amount, it's not going to really, alter the planet too much. So the consequences of decisions are sought, and the costs of poor predictions are borne by the algorithmic developer rather than the individual. Now, if I go through scenario 2, you'll see this is the scenario that I think we're operating in the environment. So the future is ambiguous. Data is sparse and uncertain. Valuable data is sparse and uncertain, despite the volume of data that we can now collect. Okay. So how did we finish up in the article? What did we say? How did we, uncertainty, does it matter? Yes, it's essential to be honest about the level of uncertainty in what we do. Because without that, we will simply not get public trust in data-driven decision-making will fail if we don't do a better job of conveying what is uncertainty. And it's not an easy task, because I've been in front of people and I've given a talk and I've said in the uncertainty quantified estimates that it's going to range from A to B, and the response I got was, I don't want the uncertainty version, I want the certainty version. So, so people see uncertainty quantification as failures of models rather than something that we need to educate them about. And we do need to educate them. So I used to pull my hair out and think, oh, if only these people took a few probability courses or a course in statistics, our problems would be solved. But no, so we can't keep complaining about that people don't understand. It's up to us as a community to try and get this message across. But, there's a plus side to all this, and I'm going to end up with a quote from Richard Feynman and think how lucky we are to live in a world of uncertainty. It offers endless opportunities to learn, and as he says here, in order to make progress, one must leave the door to the unknown ajar. And I think that that's quite uplifting to think about that there is uncertainty, and we should embrace it and not be scared of it. But so that's it. Thank you very much.